Good afternoon. This is class number 082, CIVE 634, Surface Water Hydrology. And I'm Professor Victor Ponce from Civil Engineering Department at San Diego State University. And the class today is going to be entirely dedicated to solving or explaining the answers to the midterm, which took place just this Monday on the 10th. Today is the 12th of October. So I'm going to go over and I solved the exam for all of us. And when I do grading, of course, it's an exercise in carefulness. You got to be careful because these are essay questions, and you got to read and reread the answer to make sure that it's correct. And so what I do is I look for keywords or important words in the phrase. So if those important words are there or very close to where I want or what I'm looking for, then you get full credit. And full credit is a -0, meaning full credit is 10 points. Otherwise, you get -1 or -2 or -3. Typically, I don't give more than -3 unless you really did not answer the question, okay? Which is not the case in this group. This is a pretty good group. So, so let's get started here. Number one, what are the Hadley and Ferrell cells? How do they affect precipitation across northern latitudes? Okay, the Hadley and Ferrell cells are two large-scale atmospheric circulation patterns. There is actually a third one, which is the polar cell, which is up north. People don't talk too much about that one because hardly anybody lives out there in the poles, right? 60 degrees to 90 degrees that's even, I think, beyond Canada. Well, maybe Canada borders 60 degrees. But let's be honest, very few people live in those latitudes. Okay, so the Hadley cell rises at 0 in the equator, causing increased precipitation in tropical latitudes, because when the air masses rise, they cool, and when they cool, they precipitate. Well, the conditions are there for them to precipitate. Moves north in the northern hemisphere and descends at about 30 degrees, thus causing decreased precipitation at mid-latitude. Mid-latitudes is this term that is considered 30 degrees. 30 degrees is so-called mid-latitude. Okay, so for instance, here in San Diego, we're at latitude 32, and we don't have a whole lot of precipitation, which it kind of, it agrees with it. Now, if you go to San Francisco is about 40 degrees, is a little higher, and they already have more precipitation. You go to Northern California, you get to 44, 45, 46 degrees, and it gets wetter and wetter as you move up on the northern latitude. Now, of course, latitude is not the only thing that causes precipitation, but the Hadley and Ferrell cells are of global dimension or size, so they are important. The Ferrell cell is the opposite of the Hadley cell, which rises at 60 degrees, which is the temperate latitude, increasing precipitation at temperate latitudes and moving south in the northern hemisphere, and descending at about 30. So they both descend at about 30. That's why 30 doesn't have precipitation. The Sahara, for instance, is at about that latitude. Thus decreasing precipitation at mid-latitudes. So that's the Hadley and the Ferrell cells. That's basically what I was looking for. Most of you answered this question correctly. Let's move to number 2. A, what is the main conceptual difference between the conventional water balance and the Livovich's or Livovich? What is the main drawback of the conventional method? Okay, the first thing I was looking for in here is the main difference is the concept of wetting, which was developed originally by Livovich. Prior to the work of Livovich, which I believe is dated 1979. I could be wrong. Maybe he has an earlier paper, which I have not read, which is probably in Russia. You know, the gentleman is Russian. But in 1979, he wrote a book which it was titled or is titled The Water Resources of the Earth. And I was able to grab a hold of that book when I was in India, and I read it, of course, because I didn't know at the time that there was such a book. But interestingly enough, I think the Leibovich book was already at the library here at San Diego State. We had a good library. I believe at the time when I joined, it had about 1 million volumes or items. So we had a good library, but you know, there's a whole lot of stuff out there, and one doesn't get a chance or the luck to look at this. But definitely, when I was in India, I ran into Leibovich's book. So I read it entirely. I think it was a couple of days that it took me to read that book because I was interested in what he was saying, because he was coming up with a different story. Okay. So the main difference is the concept of wetting, which in Leibovich approach is defined as the fraction of precipitation not converted to direct surface runoff. Direct surface runoff. Okay, so anything that did not go into direct surface runoff is supposed to be wetting, which later on separates into base flow, vaporization, and so on and so forth. B, the main drawback of the conventional method or the conventional water balance method is the double counting of infiltration and base flow. Because infiltration may follow either of two paths: remain close to the surface to return as evaporation and evapotranspiration, or move vertically and reach the groundwater proper, eventually to join a neighboring stream and add to the total runoff in the stream. So there is a double counting in there if you consider that infiltration is separate from evapotranspiration, which is not. Water can infiltrate and come back as evapotranspiration. So there's a double counting. When I published our Shetty paper in 1995, which I briefly touched upon, we actually had 2 papers on this subject. And I briefly touched upon a number 1 paper and number 2 paper. I didn't even cover it because it was too much. It was just too much. I would have had to spend a lot of time on it just to make it worth all of us this time. And I decided not to. But it's in there. In our first paper, in the first section of our class, is the concept, what I was going to say was that when I published this paper, one of the comments that came back from the reviewer, one of the reviewers, you know, every time you write a paper and want it to be published in a journal, you have to submit it to when you submit it to a journal. And typically at that time, I was submitting to ASCE, American Society of Civil Engineers. They only had one journal, the Hydraulics Journal, that later on in the year 1996, they decided to add another journal because they've got 20 journals in different areas of civil engineering. They added the Hydrology Journal. And I think I mentioned to you that it was on the first issue of the Hydrology Journal that our paper with Hawkins came out, January of 1996. But at that time, the Hydrology Journal was not out, so we published in the Hydraulics Journal. And that was basically it. And one of the comments of the reviewers was that hopefully this presentation or this method is going to help us solve the problem of double counting. That's what he said, which is interesting. Double counting had been recognized, but we had not really at the time not come up with a methodology. So Leibovich helped. He's widely regarded around the world. Number 3 is describe 4 important properties of water that make it unique. I wanted to stress the fact or point out the fact that we're studying water, we need to know our physical, chemical, and biological properties, not limit ourselves to the physical and or chemical. Biology is an important area of science, and engineers would do well, particularly civil engineers, if they learned more biology, even though it's really not considered to be a part of the curriculum of a civil engineer. But nowadays, in the last 30 years, the situation of practice has become more interdisciplinary, meaning we already know a lot about our own field, but we need to know a little about other people's fields so that we can interact with them. Otherwise, interaction will be almost impossible. I always say my model of education is the calla lily. You may be familiar with that flower. it is broad on top and then it narrows down, right? And it's a white flower, kind of a beautiful flower. It's called a calla lily. Okay, so the concept is that one should be broad, very broad, but not deep, so that you can understand everybody else and what they say. But you also should have deep knowledge on some subject that is your area of specialty or expertise. Otherwise, you won't be able to get a job to do work, because people would not think that you are knowledgeable enough on that subject. So like in my case, for instance, I had three or four areas that I practice, and I know a whole lot about other areas, but just a little bit so I can talk and discuss it and relate to it. Like the time we did the 800 millimeter ISO high, that required a whole lot of knowledge on various fields, but I could not have done it had I not been prepared already at the time to do it. And my watershed, or I guess my change, my transformation, was in 1979. You know, I studied civil engineering. I graduated in the year 1968. So 79, I had an opportunity to do hydrology in the Pantanal of Mato Grosso. They hired me to do a 2-month assignment, and it was strict hydrology. But once I got there and I visited the areas, I realized that the problem was not really hydrology. It was more complex than hydrology. Even though they had hired me for only hydrology, they expected me to know more than hydrology. And sure enough, I had to learn very quickly. There was a lot of things, and I mean, the time now it's not appropriate, but there's a lot of stories that I know that I learned at the time that is not necessarily related to strict hydrology. What's the difference? Hydrology is the issue of quantity. It's always been from the beginning, both cubic meters per second or CFS, or volumes, cubic feet, acre feet, or cubic meters, right? But water is not just physical chemical, it's also biological. Is the element that sustains life. So we have to be aware of that. Life is an important subject. So that is why I wrote that paper many years ago, maybe 5-6 years ago, it's dated, where I explained everything, physical, chemical, and biological properties of water. As a matter of fact, if you notice at the end of that paper, it does say that we referred or mentioned the 3 properties. And then I think I said it in this way. I said, as if Mother Nature had intended from the beginning for those 3 sciences to coalesce into one, meaning there's only one science. We, meaning society, how can I say, not society, but because there's several societies throughout the world. Science of the 1800s decided at that time to split and to separate the entire field of knowledge into several fields. And the first fields that came about were physics. Then physics was early, like Newton's time, you know, like 1670, something like that. Then came chemistry with Lavoisier out of France in the early 1800s. And then at about that same time, and then later on, came the subject of biology. So biology is only 200 years old, chemistry 250, and physics maybe 300, 350. And at that time, physicists, chemists, and biologists developed. And pretty soon, if you were a physicist, you couldn't deal with chemistry or biology. And that was interesting. The field separated and everybody kind of kept to their tent and they wouldn't communicate with each other. And that led to a lot of problems later on. Nowadays, we are earnestly trying to correct that. The communication has become really important. Take a look at Professor Ponce, your professor. Up to the year 1989, I only read 3 journals. And since 89, I learned and I told myself that I should read everything that was related to what I was doing at the time. I can't read everything. It's impossible. You know what? People don't have a mind to do that. But I started reading. For one thing, I read Humboldt because I came across Humboldt. And when I read Humboldt, I don't know exactly how I got there, but when I read Humboldt, I realized that the guy really knew what he was talking, but it was knowledge of the 1800s because he had a bunch of mistakes out there, but they were understood because at the time, science had not developed to that point. So it is a beautiful book. those of you that are interested in learning about nature and the history of nature, I advise you to read Humboldt, but it will take you a while. It took me about a year to read it. It's 7 volumes. And then later on, the book was so good that 2 or 3 years later, I reread it. So I read Humboldt twice. He's one of my heroes, by the way. Okay, so we have unique properties. I listed 5 properties, which are the properties that I listed in the paper. Its capacity for ambient temperature regulation. So wherever there's a body of water, there's temperature regulation by the body and its proximity, like oceanic climates and continental climate. A continental climate would be the climate of Idaho and North Dakota, or North and South Dakota. Oceanic climate would be California and New York, because they're next to the ocean. Floatability in solid state, we know that, and the fact that it allows life in the ocean to proceed during winter without the entire ocean becoming or changing into solid state. Surface tension and capillarity properties allows life, allows vegetation to survive, because they can pull the water up from the roots. That's the way they do it. It's marked solvent properties, dissolve everything. Water will dissolve almost anything. When you shower, soap helps, of course. Why do you use soap? That's an interesting concept. Why do you use soap? I often thought about that. Because you want to have a shower for 5 minutes or 10 minutes, however, whatever it may be. Because if you don't use soap, you'll still wash, but it will take you 30 minutes or an hour. You don't want to do that. So we help it with soap, but the water will dissolve almost anything. That is a truism that has been demonstrated. And its active relation with proton chemistry, pH, and electron chemistry, PE. Now, the pH is a very well-known subject. It's taught in high school, but the PE is not. And I myself had a good experience with this, because in 1991, 1992, I believe, I applied for a grant in NSF. That's a small grant. I think it was a travel grant, actually. There was a wetland in Brazil that I wanted to go visit. So I wrote a grant. Like, I've had funding from NSF in the past, or prior to 1991. So I knew how to do it. So I wrote the paper, the proposal, and I submitted it. I think it was $25,000, $30,000 at the time, which would be 50 to 60 of this time. And they declined it. And the reason why they declined it, one of the reasons why they declined it, is that I wrote a paper to review the status of a wetland. I don't remember the name of the wetland right now, but I was going to do wetland hydrology, as a matter of fact, to kind of begin the wetland hydrology study or problem, because not too many people were doing wetland hydrology at the time. This is 1992. And the proposal was declined. And one of the reasons for the declination, they said, for declining the proposal, was that I wrote the entire proposal, maybe 10 pages, and I never mentioned PE. First of all, I never mentioned PE. And they were correct. I didn't know at the time that this PE existed. And this was in 1992. So I quickly went into the literature and figured out that exactly I had made an omission, a great omission, and that's why I was kind of declined and not allowed to proceed. So as you can see, sometimes these things have consequences. Now we know, and later on, I read the book by Hadley, I believe, right? Professor Hadley. I believe he's at Iowa State or somewhere out there in the Midwest. He wrote a book called Wetlands. Very thick book. It's about 1,000 pages. Very comprehensive book. As a matter of fact, I use that book as a basis for my teaching of environmental hydrology. The part of the chapter on wetlands is mostly based on Hadley's book, which is a very good book, by the way. And it was very early at the beginning. I think Hadley's book must be 1995, 1997, or something like that. I could be wrong, plus or minus a couple of years. Why did Hadley write that book at that time? Well, I don't know. I don't know the gentleman. But what I know is that in 1990, the U.S. came up, or the federal government came up with the Wetlands Act, because the idea was to protect the wetlands, and they had to put it into legislation, because prior to 1990, all wetlands in the U.S. were subject to development, meaning dry them out, make dry land instead of wetland, and develop, put some buildings in there on top. And that's fine. But if you do it in excess or excessively, then you'll kill all the wetlands. And are the wetlands good or bad? The answer is they're part of nature. And therefore, they should be respected to an extent, of course. You know, there's always the issue of economics versus conservation. And that issue continues, but it'll still go around for a few more years. It'll continue to go around. There's people that propose or promote development and others that promote conservation, and they are usually at odds. So that's the story on that question. Now let's move on to the number 4. What is the main difference between the Penman and Penman-Monteith methods for the calculation of evaporation? B, did the Shuttleworth-Wallace method improve on the Penman-Monteith method? At what cost? I put in there at what cost. I thought that was kind of a tricky question. And I guess it was tricky because only one person of the class answered correctly that question. Okay, let me get in there. What is the main difference between the Penman and Penman-Monteith methods for the calculation of evaporation? The correct answer is, in the Penman method, the mass transfer evaporation rate part of the equation, because it's only half of the equation, is calculated based on an empirical formula, which was put together by Dalton. So what Penman did is that he took the energy balance and the Dalton conceptual formula and did some magic in there, which I don't think it's 100% kosher, by the way, but it was Penman's. He sat down to do it. He came up with that equation. He was not interviewed like Marcus as to how is it that you came up with that equation. I believe he actually did a couple of algebraic tricks, because I actually developed that equation. We sat down to develop that equation to make sure it was correct. And I came up with the conclusion that he had a couple of tricks in there, but it allowed him to get a simple equation that everybody understood and could relate to, because it is a simple equation. It's weighting 2 ways of doing it. And the weighting factors are very well defined, right? The theta and the gamma and the delta. So he achieved fame by doing this. And then that was in 1948. And Penman, as you know, was widely regarded as one of the most knowledgeable people in water around the world. He was a British gentleman. And then in 1966, this other fellow called Monteith came over and improved the Penman method, because he gave the Dalton formula that had gone into the Penman formula as part of the Penman formula. He gave it a physical basis. That was the importance of the Penman-Monteith. If you can find the external or aerodynamic resistance and the internal or stomatal resistance, then you have a better answer than Penman's. And that reasoning caught on so much that after a few years, I don't know how many years, maybe 10 to 20 years, the FAO, which is the Food and Agriculture Organization, which is an arm of the United Nations, adopted the Penman-Monteith method as the standard for evapotranspiration calculations, on top of many others that by that time had already been developed, like the Thorne-White method, which is an early method, I believe 1953, 55, which was not very good. It was empirical. Empirical is the lowest end of the methods. First, physically based, deterministic, then stochastic or probability, then conceptual, like the Marcus equation, or I believe the Penman equation. And then fourth, the empirical method. Suffice it to say that all methods prior to the 1930s, so it's only 90 years ago, they were all empirical. And I take that back. There's some exceptions, of course, and everything I say, there's some exceptions. Everything anybody says. The rational method presumably was developed in the year 1890, and I'm saying 1930, so that's not quite correct. We could go back to 1890 and say, prior to 1890, all methods were empirical. And the reason I say 1890 is because in 1890, the rational method came about, and the rational method was not empirical. It is a conceptual method. Okay, so it can be applied anywhere, absolutely anywhere around the world. It's a concept, right? Just like Marcus's method. How good a concept or how bad a concept, that's another issue. But the point is a concept that can be extrapolated or used throughout the world as a concept. Okay? You can disagree or agree with the concept, but it's not empirical. Okay, so that's the argument I'm sure you guys remember that I had with Professor Hawkins when we wrote the paper on the Marcus method. That I wanted to call it conceptual and he wanted to call it empirical. And I said, no, Pete, I'm sorry, I'm the lead author. I will prevail on this one. And he kind of bowed down, acknowledged that that was the case. I was pretty strong in that case. And I believe, listen, I am doing the transcript of the interview, the Ponce interview of the Marcus interview. So interview square. And I am going to finish that transcript in about a week or so. It's a long transcript. It's about 90-minute. Yeah, it's a 90-minute transcript. What is a transcript? There was an interview that was held in June of last year, which is one interview, part of many other interviews that were done with the people. The NRCS interviewed a committee of ASCE, interviewed a whole bunch of people, I don't know how many, 8 or 10, that had anything to do or that could share any knowledge about the historical development of the runoff curve number. And I was one of the chosen people to interview. So I was interviewed. And a year later, they sent me the transcript so that I could fix it. Because a transcript is an oral accounting of what went on the interview. And there's always bugs, grammatical bugs. I said something that that had to be fixed or whatever. So the author, that is me, the author, not the author, but the interviewee, that's me, that means Professor Ponce. I'm actually correcting the transcript. So when I finish that work in about a week or so, I'm going to post it on my site. So that if people don't want to go through the, as I say, through the raster, they could always go through the vector. It's the same content, only that in the vector, it's a story that you can read rather than just view it. Okay, so the second answer, did the Shuttleworth-Wallace method improve on the Penman-Monteith method? Okay, see, this is the issue here. The Penman-Monteith method had 2 resistances. Granted, they were hard to evaluate. They're still hard to evaluate. But people go about, and there's some experience, there's 50 years of experience on more than 50 years of experience on the Penman-Monteith. There's experience also for ecosystems, not just agriculture. So the Penman-Monteith is very well established. I doubted whether it will be, superseded in the future. Nevertheless, there were a couple of people working out of England, Shuttleworth and Wallace, who decided 20 years later, 1986, I believe, or 85, plus and minus 1 or 2 years, they developed a supposedly better method because the Penman-Monteith has only 2 resistances, so to speak. But Shuttleworth and Wallace said, no, there really is 3 evaporations in here. There's evaporation from the substrate, meaning the soil. There's evaporation from the lake, that's water, 100% soil, 100% water, and vegetation. And it's its own thing because vegetation's got to lift the water, pump the water from the ground, put it through the stems, and then release it at the stomata level so that it can be evaporated at that time by the normal process of evaporation. So totally, it's an entirely different process. So they decided that they were going to come up with evaluations for each one of those 3 components, which I believe is correct. That's the correct way to go. And I believe that the Shuttleworth-Wallace may well be a better conceptual method, theoretically conceptual method than the Penman-Monteith, but it has a problem. And that's why I ask here at what cost. The what cost was that we had trouble with the 2 resistances of Penman-Monteith, and now we're going to have trouble with the 5 resistances of Shuttleworth-Wallace. So to my knowledge, it has not been adopted. If it's adopted, I don't really foresee that happening because of the KISS principle. You heard me talk about that. The KISS principle says, keep it simple, stupid. Meaning the simpler the method, the more people are going to use it. The reason, I don't want to get into details, but that is a fact. That is a fact. That's one of the fortes of the runoff curve number method because it is simple. You can use it, you can misuse it, but it's fine. It has a whole lot of people that will swear by it because you get a number quickly. And furthermore, it is a number that is supported by the government, or the federal government. So if anybody tries to argue with you, all you need to do is, I'm sorry, MACUS was adopted 50 years ago by this document, which is a federal document. So it has the how can I have the support of a federal agency, and that is enough, particularly in a court of law. And you know, there's a lot of instances where engineers have to defend their thinking in courts of law, the so-called expert witnesses and so forth. You know that, or at least you have heard of it if you have not participated in one of them. Okay, there's stories about that, but I'm not going to get into that. So number 5, how did Marcus arrive at his famous equation for soil loss? What does the equation do? Okay, so this is a fundamental equation that all of you should be very aware of. Well, the first one is a historical thing, because, I mean, people could say, I don't care how he got it, but he got it and he published it and he was accepted. But the point is, for a historical purpose, and I say in there, as Vic Marcus told Professor Ponce in the now famous interview, it is famous interview, by the way, I'm not exaggerating in here. Everybody around the world has read that interview. And I have a lot of friends and acquaintances around the world that have read the interview and have called me to congratulate me on it, on its content. So I arrived, that's what he said, Marcus said, I arrived at the equation one evening after dinner, seeing that it fitted the data very well, and after having tried many other alternative relations. So there must be something behind the equation as compared to other equations that he had that did not do as well with the data. That was it. Why was I interested in getting that at the bottom of this? Because I think I mentioned to you that I was in India and I was asked the same question by the Indian engineers. They said, how did this equation come up? Can you tell us? That was 1991. I had just barely finished writing the book, 1989. And I confided to you, and I'll squarely say that when I wrote the book in 1989, I copied the equation from the NIEH4, the manual, and didn't ask too many questions. Why would I want to ask any questions? I was writing a book transcribing what other people had done. It was not my research. So I just copied and put it in there. But then I got a chance to go to India, and the people out there didn't want to take my word for an answer. They want to know the reason. So then I put it in the back burner. I said, whenever I get a chance to, I'm going to really research this. And I got a chance 5 years later when I interviewed Marcus. And that was my intent, to go there, interview him, and I was successful in actually finding him and convincing him. There was a trick that I used, and I think I revealed the trick already, but I did convince the gentleman to talk to me. I basically told him I'm from California, very far. If I move west, I'll run into the ocean. So the farther you are, the more friendly you could be. And that was a fact. So then Marcus agreed to talk to me. That was great. That was great for me and great for the profession, by the way, because he never talked to anybody after he retired. And he died a year or two after I met with him. So I was lucky that I was there before he passed. Okay, so then what does the equation do? That's important, very important. The equation is a nonlinear fit, definitely a nonlinear fit to the rainfall runoff data. For a given soil of certain curve number, as P increases, the amount of soil storage, which is P minus Q, asymptotically reaches a maximum value S. There's a correct statement, and that is the characteristic of Marcus's method. No other method that was around had this characteristic. And this is a fundamental concept because it implies very strongly that there's a certain amount, a maximum amount of soil storage, which is correct, because below any soil, there is rock. It's just a matter of depth. The rock sometimes is at 10 feet, typically, but it could be at 60, 20, 100, you know. There was a case in Nevada, I believe, when they were citing the nuclear waste plant, or where they were going to put the nuclear waste. I don't know if they proceeded with that project, but But one of the comments I think was that the soil was very deep, and they were concerned about this and that. The point is that the depth of a soil is important for various considerations. There's always rock under the soil. No question about that. You cannot have infinite soil. Obviously, eventually you get the rock, different kinds of rock. Igneous, metamorphic, sedimentary, but rock nevertheless. And so that's the answer. Number 6, what sets Marcus's method apart from other soil infiltration formulas such as green and amped? What is missing from the physically based infiltration models? Okay. Answer to A is, while Marcus's method has a finite value of maximum soil storage, the green and amped infiltration formula has no such limit, featuring instead an infinite amount of soil storage. Therefore, while Marcus's method is suited for modeling saturation over land flow, the green and amped formula is better suited for a bottomless infiltration model such as Hortonian overland flow. Now, the issue of bottomless is something that I believe I came up with. I said the difference is this has got a limit and the other one has a limit, doesn't have a limit. It goes to the bottom and the bottom is infinity. So I call it bottomless. Our colleague, Roger Smith, didn't quite like the way I said it. And of course, he didn't like it because he had practiced all his career doing the green and amped equation, and he didn't want it to be characterized as bottomless, which it was, by the way, as opposed to the soil conservation service method, the Marcus method, which was not bottomless. Now, the issue for us, the more important issue is the soil out there bottomless or is it limited, as Marcus said? And the answer, 99-1, is Marcus was correct. So from that standpoint, Marcus equation, the SCS equation, and NRCS equation beats the green and amped. It beats the green and amped, in my opinion. And this is some of the arguments that we put into the closure, if you would recall. I did not put a lot of stress into the closure, but if you wanted to, you could go back and read it. It's on the record. It's on our syllabus. The discussions by Roger Smith and others, particularly Roger Smith's discussion, which was a little bit, should I say, belligerent? Yeah, I think it was a little bit belligerent, but not too much. He finally realized, to his credit, that he couldn't criticize us too much because everybody's using it. 99-1, to be honest with you, okay? Because in practice, nobody uses the green and amped. The green and amped is used in research, and there's some room for it. But I do believe that in practice, it's the Runoff curve number. The problem with the Runoff curve number is very simple, and that is a strength and its weakness. It's a strength because it is simple, it's easy to use, it's very reproducible, repeatable, right? Can be repeated. While the other methods, such as the green and amped, if you vary this parameter, if you vary that parameter, which has not been indexed or classified, there's 3 parameters out there, and you can pick up any number that you want. So you really can get any answer out of the green and amped. While out of the curve number method of Marcus, you can only, with the given curve number, you can only get one answer, period. 68 gives you something, and that's it. So there's something to be said, or a lot to be said, about reproducibility for court cases and for all this sort of thing. So science is good. I'm a scientist, also an engineer, but I'm not going to go 100% for science when I know that there's a practical issue out there that needs to be resolved. So in here, our colleague and friend, what's his name? Roger Smith did not win on this one, meaning he had to agree that from a practical standpoint, the Marcus method was better. Okay, and what is missing from the physically based infiltration models? Right, most soil have a practical limit on depth, but this is missing from the physically based models such as green and amped. Something that is also missing from green and amped is the holism, but I didn't put it in there because holism is also missing from the Runoff curve number. Sure. So holism is a high call. Holism means include vegetation, include a whole lot of other things, there's a physical chemical processes like crusting, that is not met either by moccasins or the other guys. So crusting is a tough problem. Crusting happens, for instance, here in California. If there ever a fire, I shouldn't say if there ever a fire, because in California we have fires all the time. But fires in Chaparral produce crusting. That everybody knows. Professor Kinoshita, who many of you know very well, you may be working with her, as a matter of fact. She's one of the national experts on fire hazards or hydrology after fire. Yes, that's what he has studied over, I don't know, maybe 5-10 years. So it's important. There's a lot of work in that area too. We have not covered it as part of this class, but I can refer you to the literature. You should Google out there, soil crusting, paving, that causes or happens a lot in this area where there's a combination of fire, forest fires and so forth, and chaparral. The story on that fire vis-a-vis chaparral is very complex and very extensive. I don't have the time to talk about it at this time. Maybe at some other time. Okay, number 7. How does baseflow vary across the climatic spectrum, from super arid to super humid? B, why? Okay, the answer is in super arid regions, the streams are typically ephemeral with no baseflow. Conversely, in super humid regions, the streams are perennial with baseflow constituting a large portion of the total discharge. In the Amazon, the largest river in the world, baseflow is about 50% of the flow. 50%. The floods are large, but they're large in volume, but not in peak, because they're highly diffused anyway, because the river has a very mild slope, bottom slope. And we know from hydraulic studies that every time you have a mild bottom slope, you're going to have a lot of wave diffusion of the kinematic wave and so forth. We're going to study that later on in more detail. And therefore, you're not going to have a whole lot of peaks. Peaks are going to disappear completely. In the Amazon, you don't have a peak. Actually, there's a peak, but it's a peak that lasts 2 months. What kind of peak is that? Typically, when we talk about peak, is a peak that lasts a few minutes, the peak of the flood, or maybe an hour or 3 hours in a small region, but not in the Amazon. So the Amazon is the place where you have perennial flow because it is mostly base flow. Like I said, in the Amazon, it's about 50% always. Even if it doesn't rain, you'll still 50%. While in the super arid regions, super arid and arid regions, the streams are typically ephemeral, meaning they don't have any base flow. That means that the base, what actually means is answered in the second part of the question. Let's take a look. The reason why base flow varies from near zero at the dry extreme of the climatic precipitation spectrum to very substantial in superhumid regions is, and I was looking for this, by the way, very few of you answered this question correctly, by the way, or completely, is the position of the groundwater table relative to the stream bottom. If the groundwater table is below the stream bottom, you will not have base flow. And the groundwater table is above the stream bottom. So this means that in the Amazon, the groundwater table is right there on the surface, within a foot. And it is correct. Well, if you go to any other place that is semi-arid or super arid, the groundwater table could be maybe 10, 20, 30, 50 feet below ground. And if you have the river does not get to 50 feet elevation below ground or below the top, it will not reach the water table. And if it doesn't reach the water table, it will not drain the water table. An interesting story about this issue. Back in the 18th century, we, meaning society, did not know the hydrologic cycle. We didn't know. We saw the rivers, fine, everybody know the river, but we didn't know where it came from, how did it work, and so forth. We know that it rained, and when it rains, the water collects and it moves onto the surface. That was easy to figure it out. There must have been a knowledge that was around for at least 2,000 years. But the essence of how the hydrologic cycle works, we did not know because we were missing the base flow component. How could we miss the baseflow component? Because we don't see it. Simply, we don't see it. The baseflow is coming out at places in locations where typically most people don't see it because it infiltrates slowly but surely, right? So we didn't know. But there was a gentleman of French origin. I believe, I don't remember his name right now. He is listed in the book by Inche. Professor Inche of University of Arizona, wrote a book about 30 or 40 years ago, and he called it The History of Hydrology. A book which, by the way, I confess, I have not read. I should. A couple of years ago, I tried to get it at Amazon, and somehow I couldn't get it, so I gave up. So I'm still looking. What I would have to do is go to the library and check the book out or do something about it. I am going to do that now because I have a lot of reading to do in the next couple of years, as you guys probably realize. I'm going to have a lot of free time starting in January. Okay, so this gentleman came up in the middle 1800s. So that's 250 years ago. No, in the middle 1700s, 250 years ago. He says, I got it. Eureka. The water in the river, if it's not raining, it's coming from the ground. That's what he said. That's what he said. That's what Inche said in his book, that he was the first gentleman that put it in writing that the water, when it's not raining, is coming from the ground. Isn't that fascinating? Well, it is. It's history. And that's the essence of this answer, by the way. The position of the groundwater table relative to the stream bottom. That is why the base flow varies. If it were not the same, if it were not varying, the base flow, the position of the groundwater table, every river would have base flow, which is not the case. I think I've shown you pictures of that. Number 8, what 4 variables are included in the formula for theoretical time of concentration of overland flow? This was the easy question, by the way. Most of you, if not all, answered that question, this question. The variables that are included in the formula for theoretical time of concentration are the following. Plane length, obviously the length, because there's a certain time in there involved for the travel of the water from the top to the bottom of the basin. Roughness coefficient, the speed would depend on the roughness coefficient. And we use, interestingly, we use Manning's. How fascinating. I'll get to that in a minute here. Number 3 is plane slope. Right, the slope determines the speed at which the thing travels. And effective rainfall intensity. Yes, that also comes in there. The plane length and n are in the numerator because they increase the time. The longer the space, the longer the time. The longer the Mannings, the longer the time. And the slope and the intensity are in the denominator. So most of you answered this question correctly. Now, this basically dwells or covers several points of discussion that I had when I was teaching this at the time. For one thing, we talked about the Papadakis Kazan is the first equation that has all 4 ingredients. Technically, there's 5 ingredients, but most people recognize only 4. The 5th ingredient is the exponent of the rating, which is somewhere in there according to the theoretical time of concentration. But in my book, in chapter 2 and 5, I believe, no, 2 and 4. In chapters 2 and 4, I discussed the time of concentration, and I also discussed the overland flow, and we have covered that ground in this class as a review, of course. And we're basically saying that that these equations are similar. The theoretical equation for time of concentration of kinematic overland flow has the same elements as Papadakis Kazan formula. Now, Papadakis Kazan formula was correct. The difference is that the Papadakis Kazan formula is an empirical formula with conceptual elements, but finally an empirical formula. What Papadakis Kazan did was Papadakis was head of the department at Colorado State University at the time. I had already left. This was 1984, 85. And one day he visited, he was a friend of mine, a colleague actually. He visited in San Diego at about that time, by the way. And he told me that he was writing this paper, and he then subsequently, I saw him present the paper, I believe in 1987 in Maryland, somewhere, University of Maryland. And he told me that he had hired a student because he was a professor, and the student collected all the data available, a lot of painstaking work, and they correlated all the data and came up with this equation. And I thought it was very good contribution, because up to that day, there were two equations. There were two equations for the calculation of time and concentration. The Kirpich formula, which only used L and N, and the Kirby-Hathaway, which used L, N, and S. But none of them included all four components like the Papadakis-Kazan did. So I do believe that Papadakis-Kazan 1987 is the first equation that came up complete with the four elements. And it was empirical because they based it on data. They based it on data. And by the way, the empirical data was kind of similar to the theoretical. But I do believe Papadakis did not mention that in his paper. I could be wrong. And I believe the Papadakis-Kazan paper is part of our reading anyway. I could go back and review it and see if he did say at the end of his paper that his empirical equation had everything in its place and that it kind of resembled a little bit here and there the theoretical formula. Not to say, and I'm going to confess it here, something interesting, that because the theoretical formula is the best formula. No, not necessarily. And we've proven that already. The theoretical formula is a good formula. It sounds good. It feels good, but it does not necessarily represent everything that's going on in the field. And that's why the empirical formula of Papadakis has a different kind of strength, but it does have strength. This is what Woolheiser had said in his paper that we have read in this class. The El Dorado paper, remember? We read that paper briefly. That's what he said. He said, no matter what we do, we're always short because we're not reproducing in the laboratory exactly what's actually happening in the field. That's one of the contributions of Woolheiser after 30 years of doing this work, day in and day out with the Agricultural Research Service. Okay, equation number 9. What is surface albedo? How does surface albedo affect the amount of precipitation? Surface albedo is the coefficient of reflectivity of a given surface towards short-wave radiation, the ratio of reflected to incoming solar radiation. Short-wave radiation is mostly the visible radiation, the sun rays and stuff. So how much it reflects, actually I take that back. The short-wave radiation is a little more than the visible radiation. It's in the spectrum, it's a little wider. It's all in my book, chapter 2, by the way. And the graph is out there of electromagnetic spectrum from the very short to very long waves. So the coefficient of reflectivity. Why is this a fundamental parameter? Because it determines how much life is going to be happening on the surface of the Earth. Because if the entire power of the sun waves or energy returns to space, there's nothing left in there to propel or to power, or for the energy to power life processes. So very important, some of it be left in there. And the average albedo of the Earth is 0.15, calculated by Otterman and others. That means 15% stays and 85% somehow leaves. It goes back to space. And out of the 15%, it's been documented that only about 2 to 3% are actually used by the plants. So that means the other part that's missing, it's somewhat lost somewhere, actually. You can, if one wanted to do a complete energy budget, you could actually evaluate for certain times and times of the year and so forth, and spaces, locations, what is the actual partition of how much went in, how much stayed, and how much of that energy that stayed was actually used in a productive way. Because there's also the unproductive evaporation, like the evaporation from a lake is kind of unproductive. Evaporation from ground, unproductive because it doesn't produce food for us or landscapes or whatever. We call it unproductive, but in reality, it's not unproductive because there's desert biota, desert ecosystems, and if you don't like deserts, so be it. But the point is that they were put in there by nature, so we got to respect them also. Okay, I told you many times that my own country, Peru, is It has a strip, the entire coast from north to south, 12 degrees latitude, 12 degrees latitude. It's a desert. It's about 20 kilometers, a strip of 20 kilometers. It's a complete desert. It's the driest desert in the world, or among the driest desert in the world. I have not made any comparison between the Peruvian desert and the Sahara, or this desert in northern Chile, which I believe is widely regarded as being the driest because it doesn't rain at all, anything out there. I think in the Peruvian desert, it rains maybe, say, centimeters or millimeters. I would say maybe 50 millimeters, which is 2 inches, as opposed to the rain in San Diego is 10 inches. You see, so it's much less. It does rain, but so small that actually in some places out there, it doesn't rain at all. Because if it rains, you'll have a little greenery, no matter how small. And there's some places out there that you can, for miles at a time, you can't find one iota of vegetation in the coast of Peru. I can show you pictures. I've been there many, many times. Okay, so that's surface albedo. How does surface albedo affect the amount of precipitation? This question was designed to see if you understood the process, because it's very important. Lower albedos absorb more solar radiation. Higher albedos absorb less solar radiation. Thus, a surface with low albedo, such as a rainforest, will release more energy as heat because it absorbed the energy and it's got to release it. Will release more energy as heat than a surface with a high albedo. Why did I say it has got to release it? Because it has to, because if it doesn't release it, it'll burn. If it doesn't release the heat from day to night, it'll burn. So Mother Nature made the world round and the sun on the side. So she would know that when the world rotates around the sun, half of the time it is cooling and half of the time it is warming. And it has to do that because if it warms too much, it'll burn. It'll destroy itself completely. So that is why we have, I'm joking here, but I'm serious also. That's why the world is round. So they can rotate around the energy supplier, the sun, and cool during the night while warm during the day. Otherwise, it will be hell. We will warm up and not be able to stop, and then everybody will burn. Right? That's the way it is. Additional lifting of air masses produced by the heating from below due to low albedo will generally lead to additional more precipitation. That is in my book, by the way, in chapter 2, I believe. Okay, number 10. What is the El Nino? And B, to what do atmospheric scientists attribute the root cause of El Nino? Straight out of the book, El Nino is a global climatic anomaly produced by a weakening of the trade winds along the tropical Pacific. That's why it's called ENSO, Southern Oscillation. This was studied by British people back 30, 50, 60 years ago. And they related the El Nino effect, which was an entirely empirical phenomenon discovered or named in the 1890s by Peruvian fishermen. But then in the 1930s, 1950s, the subject or the topic was taken up formally by British and I believe Swedish scientists. It could be Swedish or Northern European, where they studied this very carefully and they had the minds of actually put it all together and they said, well, this Southern Oscillation is an El Nino really. So that's why they call it El Nino Southern Oscillation. And El Nino, of course, we know now, because we studied this, the history, it comes from the child Jesus, because El Nino had a way of happening around Christmas. Why around Christmas? Well, because the world rotates, and it must be that that was the time where things got all together to produce the effect. But of course, we already know now that it doesn't happen every Christmas. The frequency is 4 to 7 years, and not every El Nino is strong or cause a lot of damage. So every second or third El Nino will cause a lot of damage. The record shows that 1983 was very damaging. 1993, another one, 1993 had this huge flood in East County, San Diego. They had never seen, and it has never recurred, a flood like that, 1993. The same flood that caused the problem in Tijuana, which we were talking about, I believe, No, it was in the other class. I get confused. It was in the sedimentation engineering. So those of you, 6 of you, I believe, are taking sedimentation. So you will relate to the issue of the Tijuana detention basins, right? That happened also in 1993. 1993 was El Nino year. Then there was 1998, and then 2017. So we haven't had any right after that, we haven't had any. So I believe that it will take maybe 12 to 15 years from 17 to come back. I believe by 1930 or 32, we'll have another El Nino again. Interestingly enough, El Nino covers the entire Pacific. It originates in its focus, or I guess you could say its center, is off the coast of northern Peru, particularly in the city of Piura in northern Peru, large city. Piura is about maybe 300,000, 400,000 people. This is the 3rd or 4th largest city in Peru. And everybody knows that when El Nino comes, and it is pretty strong, he'll flood downtown Piura with 1.5 meters of water. It sit there for a couple of days until the gradient forces it to move somewhere else, right? That's bad. It is bad, but there's nothing we could do about it. We could move Piura, but we're not going to do it. We can't do anything about El Nino. That's a global phenomenon. So we can adjust, attenuate. Attenuate is the word. Diminish, but you cannot fight completely with El Nino. You cannot fight frontally with a global climatic anomaly. At least we cannot do it now. Maybe in the future we will, but I'm not talking about the future. Okay. The root cause of El Nino is not known with certainty. Atmospheric scientists attribute it to large-scale teleconnections emanating from the groundwater regions of the mid-Pacific around the equator. This is interesting because the atmospheric scientists talk about the large-scale teleconnections. And I put it in there in our writing because we researched this. Mr. Shetty did all this work in the year 2002. He was my co-author. The large-scale teleconnections. They failed to mention that the world is actually cybernetic. So the world knows what it is doing. Mother Nature in the world knows what it is doing. So if it goes in one way too much, it immediately tries to go the other way to compensate and to balance out. And that's exactly what El Nino is doing. It is a teleconnection between the water in the ocean and the atmosphere. And they have to be teleconnected because they're part of the one system, the world. It has atmosphere and it has, which is large, as you know, and it also has the ocean. So the teleconnections between ocean and atmosphere produce these instances of this phenomenon, which is called Southern Oscillation, El Nino Southern Oscillation. It's a compound word that refers to the origin or the original name, and then later on the scientific name of the Southern Oscillation along the mid-Pacific, which we have already studied in detail. Next is, what is drought persistence likely to peak around the middle of the precipitation spectrum? Now, persistence is not duration, but it is true that the longer the duration, the more the persistence. That is a fact. Persistence relates to how many years, okay? I guess there is a little slight differences in definition there, or of color, I guess you could say, between persistence and drought duration. Likely to peak around the middle of the climatic spectrum. This is a fascinating thing because when we were doing this work in the year 2000 with Erkan and with a couple of other people, it was not only Erkan, it was Ponce. So it must have been done in the year 1997, originated because Ponce was with us in the year 1997 for 4 months. He was a drought expert from India. He had studied droughts for 10 to 20 years, so he knew a lot of droughts. When he came to San Diego State, I said, what do you know? And he says, drought, because you know there's 100 hydrology types, and you only know 1 or 2 or 3. So I asked him what did he know. He says, droughts. Okay, we're going to do a paper on droughts, because by that time, I had already developed my knowledge on droughts. Because don't forget, I mentioned to you that until 1989, I was a flood expert. And then when I studied base flow, I got interested in the other side of the coin, which is droughts. And then by 1993, I was studying droughts, 1997, and so on and so forth. And that led to the year 2000. And we came up with this paper that we wrote with Erkan and Ponce, the gentleman from India, and Erkan from Turkey. So, and we found out through a lot of research that Idaho, in the middle of the country, had the more persistence in droughts. That the droughts did not persist in other regions, no matter where in the world. We found them here in the United States and maybe in some other places around the world, but we didn't get to that data. We had access, quick and ready access to the data in India because of the Indian gentleman that was working with us. We also had access in the US because that's easy way to get the data. By that time, we already had the beginnings of what it was called the web online work. So we were able to support ourselves with that. A story that in the year 2002, when I asked Sherry to do the El Nino report, I went on vacation. I said, Sherry, you work on the El Nino and I'll come back in 2 weeks. And he did. And he told me he had consulted more than 1,500 references at that time. He himself had printed and consulted for 1,000 to 1,500 references on the web of the time, because now it's 2022. If you wanted to do this a very good job and you know what you're doing, you probably end up with twice as many references. There's a lot of wealth on the web. And you got to be careful because not all of it is good. You got to be careful with the quantity. It's quantity, but you got to call or get the quality out of the quantity out there, and it can. Typically, if you know what you're doing, you will always get quality out of quantity. That's what they did at Colorado State. They produced a whole lot of PhDs in the 70s. And if only 10 to 20% of those PhDs were good, they already had a lot and they were ahead of the game. That's what's their game, quantity. Okay, so in here, let's go back. What's the answer to this question? To be honest with you, this is a tricky question. This was the only tricky question of the entire paper or the entire exam. And I do believe, I'm not sure at this point, I'm not perfect, but I do believe none of you answered this question correctly, fully and completely. Let's see what we say. Drought persistence is likely to peak around the middle of the climatic spectrum. Because, why because? Because the answer is why. Because in an arid climate, to the left, droughts are more frequent. And since they are more frequent, they have to be necessarily of short duration. If you have a frequency of every 3 years, you can only aspire to have a drought of 2 years. You cannot have more than 2 years because the third year is a flood, or actually say 3 years. So the shorter the frequency, or the faster the frequency, I guess you could say, the repetition or the coming back of the drought, the less you're going to have, you're going to be able to add the years. There are not that many years out there because the frequency is more frequent. The droughts are more frequent to the left of the climatic spectrum. Why? Because of the aridity. The aridity causes more frequent droughts. No question about that. We know that in Russia, they have a lot of arid, ex-Soviet Union. We checked a lot of the data over there because they have a lot of arid country out there, and the northern parts are all arid. And they were reporting every 2 years, 2 to 3 years droughts consistently. So that's where we got the idea that in the arid, which is true, by the way, in the arid part of the climatic spectrum, droughts are going to be more frequent. Okay. Conversely, and because they're more frequent, they're short, and because they're short, they're not that intense or persistent. Conversely, in a humid climate, to the right of the climatic spectrum, by the time you get over to say, for instance, in the United States, you could talk about the Carolinas, you know, Georgia, and so forth. Those are humid regions. In a humid climate, which typically feature more than 4 months of rainy precipitation, that's the key. 4 months, 6 months of rain, then you're not going to have a drought because there's too much water. In the Amazon, the drought, we estimated it is 100 years. And why did we say that? Because we found one reference that said that they sensed a drought in the Amazon 100 years ago, and the drought was measured by the decrease of the stage in, I believe it was Manaus, Brazil. It decreased. It was the lowest stage. The lowest stage that every year there's a flow and the ebb of the Amazon, and Manaus is where they measure it, among other places. Manaus is kind of in the center of the Amazon River. They measured over there, and one time out of 100 years, they hit a bottom. And that's recorded, and it's part of the record, by the way. You can Google it and find it. So I came up with the idea, which is a very round number, that every 100 years, you'll have a drought in the Amazon. And that's supported by data. It's a very round number, very nice number. Okay, so we get the conclusion that if you go wet, you're not going to have persistence because it's too wet. A place where it rains 6 months out of the year, it's going to be very hard for it to develop into a drought or develop a drought, you see? So then drought intensity and thus persistence, because the intensity is related to the persistence, meaning how many years, that's the intensity, is poised to be greater around the middle of the climatic spectrum. And that has been documented by a lot of people, by the way, particularly US researchers that have done drought studies, intensity, duration, frequency, all over the United States. There's many articles on that. Okay, so the drought intensity is greater around the middle of the climatic spectrum. Now, there are some exceptions. The issue of the Sahel. In the Sahel, the drought started in the year 1970, I believe, and it went on for 15, 16 years. And it's been documented too. And why did it go on for so long? Because there was the issue of anthropogenic effects. They were doing the so-called negating the transhumance. You remember I talked about it briefly. The transhumance was the effect covered on the web, by the way. I learned this on the web. Now, when the web was already developed, they talk about everything. They put everything on the web. 10 years ago, everybody started putting everything on the web because they felt that's the only way to get to the people quickly and readily. So the transhumance was the act of people moving with the weather, moving with the season up in north, the Sahel. They would go to the border, the Sahel border with the Sahara when it was wet, the wet season, and then when it was dry season, they would come down to the border with the tropical rainforest. A couple 100 miles, so be it, or kilometers, and they were doing this, and they were nomads. That's the key to this whole thing. They could move around because they had to follow the crops and so forth. But then once the word nomad became something of a, should I say, a bad word? I don't like to talk about it, but that's a fact. As opposed to sedentary. Sedentary means you're fixed in one place like all of us are, okay? Nomad is like you could, like the teepees and the Indians and so forth, they were following the buffalo, okay? So if you're gonna do that, you gotta be moving, you gotta have the capability to move around quickly. And that's what the original American Indians were doing in the plains. They were following the buffalo, supposedly. I'm not an expert on that, but an expert on this, but that's what everybody says. Okay, so I'm going to stop there because I only have, actually, I ran out of time. But the last one is an easy one. Describe the concept of the 800 millimeter ISO height. I repeatedly have talked about this. This is a creation of my mind. I am hoping that it will be picked up. It has a lot of issues that some people have told me, are you kidding me? Forget it, that's wrong. No, not really, nobody has said that. They can't really argue with the concept. But what they could argue is its practicality. I mean, is it okay that all of us move to the 800 millimeter ISO height, which, by the way, in the United States is in the middle of Texas and the rest of the country, and the rest of going north, like Kansas, Oklahoma, yeah, whatever, okay? Or in California, it would be anywhere from San Luis Obispo to Marin County, out there somewhere. Okay, everybody move out there. That's not going to happen for the simple reason there's politics, and people are going to say, heck, I don't want to move out of San Diego. San Diego is my life. I grew up in here and so forth. So we're not going to do it. That doesn't stop the issue of rationality, of thinking about what is the more sustainable way of doing it. And that is my point. This is sustainable because it does not lead to a lot of transfer of water, and it does not lead to a lot of transfer of salts. Think about that, because it's both of them. Now, all of you missed the salt part, but not the water transfer, etc. I gave some credit for what you had said in the report or in the exam, but that's the issue. The transport of water by means that are fossil is not good, is not sustainable. And that is what Reisner said in his book, Cadillac Desert, more than 20 years ago.
I read it there, by the way. And then he kicked the bucket, died young, by the way. Reisner wrote a book called Cadillac Desert, which all of us that are interested in water in California should read, by the way. And then the issue of the salts. The salt is another issue. And I don't want to get into a sidetracking here to a very tough subject, but that's the issue of the Salton Sea, which we have briefly covered in, I believe, in this class or in the other class. Now I'm getting all confused. But I talked about the morphology. I believe that was in sedimentation, right? So 6 of 7 of you are going to hear that, or I had already heard me talk about that. The Salton Sea, one of the greatest problems, environmental problems of California, created 120 years ago by a whole bunch of people, a bunch of people that really wanted to do things from an economic standpoint. But at the time, they could not or would not realize that there was a price to pay. So 120 years later, now we're beginning to realize that we got to come up with the cost of that issue and what are we going to do about it. And to be honest with you, I've been dealing with this subject since 1997. So there's 25 years that I've heard all kinds of people expressing themselves positively or negatively on what to do, this or that. But to this point, the Salton Sea has not been solved, and it will not be solved, in my opinion, in a way, in a solution that most people, what are we going to do? Can we put $100 billion here and fix it? If we have the $100 billion, we could do it. If we have the political will to do it, yes. But that's not going to happen. First of all, people are going to disagree as to how much money. And second, are those $100 billion are going to be used properly? And what is properly? That's the issue that needs to be discussed. So with that, I'm going to leave you thinking about that. There's a lot of talk about it, Salton Sea fixing right now. And the governor of California is trying to do a lot. There's committees working on it throughout the states. In my opinion, it's going to be next to impossible to fix. But it'll get fixed by itself without us not doing anything. But it will take some time. I'd say maybe 40, 50 years. Thank you very much.
Thank you.
Thank you.
Thank you, Professor.
Bye-bye.